You know, in every single device you own, your phone, your laptop, even your car, there's this entire hidden universe of complexity. We see the slick glass and metal on the outside, we tap on the bright screens, but the real magic, it's happening on a scale that's almost impossible to wrap your head around. So let's dive into this unseen world that really powers our own.
Right. We all know what this is. It's the processor, the brain of the whole operation, the silicon heart of our digital lives. We all know it's incredibly powerful, but here's the thing. Its power means nothing if it can't talk to everything else.
So that's the big question, isn't it? How does this impossibly complex chip, with connections measured in nanometers, actually connect to your screen, to the memory, to everything? What's the invisible bridge that makes it all work? Well, that's the journey we're going on today.
Okay, let's start by zooming way, way in. We're going to peel back the layers and see what's sitting directly underneath that powerful chip. Welcome to what you can only call a microscopic metropolis. This right here is the key to everything. It's called a flip chip carrier, or more commonly, a substrate. And you can think of it like a universal translator for electronics. It takes the incredibly dense, microscopic language of the processor and translates it into a language the main circuit board can actually understand. It is the absolute critical link in the chain.
And wow, this image just shows you how wild that translator really is. What you're looking at is a cross-section of one of these substrates. It's not just a flat surface, it's a multi-level city of copper highways, weaving and connecting with just mind-boggling precision. So how on earth do you build something this tiny and this complex? Well, we have to zoom in even further. Let's take a look at the incredible manufacturing method they use, called the semi-additive process. Building this stuff is like a delicate dance of chemistry, light, and lasers. You start by laminating these special films on. Then you drill impossibly small holes with a laser. Then you have to seed the entire surface with this whisper-thin layer of copper before using light, kind of like photography, to create a pattern. Only then can you plate the actual copper pathways. It's this painstaking layer-by-layer construction. And here, you can see that process brought to life. On the left, that's one of those microscopic holes blasted by a laser. Then on the right, that exact same hole has been turned into a perfect copper-plated tunnel. They call it a via, and it's what connects one layer of our microcity to another. This is engineering at the micron scale, and it's just awesome.
But here's where our story takes a really interesting turn. Back in the early 2000s, for very good environmental reasons, the electronics industry was told to stop using lead in its solder. And this was a great move. It solved a major health problem. But as we're about to see, it created a whole new set of engineering headaches. To really get the problem, you gotta compare the two. The old leaded solder was, from an engineering point of view, fantastic. It melted at a lower temperature, it was really flexible, just great stuff to work with. The new lead-free replacements? Well, they're stiffer, they're more brittle, and they need higher temperatures to melt. That's a triple threat to reliability. But most importantly, as we're about to see, they are prone to forming these things called voids.
So this is the old guard, a beautiful, solid, high-lead solder connection. It's strong, it's flexible, it's super reliable. This was the gold standard for decades, and for good reason. It just worked. And then there's this. This is the troubled successor. Just look at those giant bubbles inside. Those are voids, pockets of trapped gas that form during that high-temperature soldering. And every single one of those bubbles is a weak point, a potential point of failure that can compromise the entire connection. But that's not the only challenge. As all of our devices get smaller and smaller, another really bizarre problem has popped up, especially in the world of mass-produced consumer electronics. I mean, just look inside a modern phone. Every single millimeter of space is precious. Components are packed in tighter than ever, and some of them are so small now, they're literally like grains of sand. And this incredible density creates brand new, really delicate manufacturing challenges. So check this out. When a component is this tiny, the surface tension of the melted solder on each end has to be perfectly balanced. If one side melts just a fraction of a second before the other, that surface tension can literally pull the component up on its end, just like a tombstone in a graveyard. The connection's broken, the circuit is open, and the device is dead.
Okay, so this brings us to a really, really important distinction. The circuit board inside your TV remote is not built to the same standard as the one that controls the airbags in your car. The entire philosophy, the cost, the manufacturing, they are worlds apart. So take a look at these two boards. On the left, you've got a super dense smartphone board. On the right, an automotive board. Now, which one do you think is harder and more expensive to make? The answer, it's probably not the one you think. Yeah, it's the one on the right, the automotive board. That board demands absolute, unquestionable reliability. And to get there, some of its internal copper layers are 400 micrometers thick. That is a massive amount of copper, which makes it incredibly difficult to manufacture, but also unbelievably robust. The industry actually has a formal system for this. Class 1 is for your everyday consumer products. If your video game console dies, it's annoying, but that's about it. Class 3, though, that's for high reliability systems, medical devices, aerospace, that airbag controller. For these products, failure is simply not an option.
And all this brings us to the final and maybe most crucial takeaway. The gap in quality and manufacturing standards across the global electronics industry isn't just big, it's an absolutely massive chasm.
This is what a lower quality Class 1 board can look like up close. You can see the copper traces are all rough and uneven. Now, does it work? Sure. But is it going to be reliable for a decade under extreme stress? Absolutely not. For a lot of consumer goods where the price pressure is intense, good enough is the standard they're aiming for.
This quote from one of our sources really just says it all. The difference in quality, in care, in materials, and in the process control between a mission-critical Class 3 board and a cheap, disposable Class 1 product is, quite literally, like the difference between heaven and earth.
And that kind of leaves us with a final thought, right? We live in a world that is built on these invisible connections. From the phone in our pocket to the plane we fly in, we are constantly, unknowingly betting on their reliability. The real question is, do we truly appreciate the incredible hidden engineering that keeps our entire world from falling apart?